Okay, so let's look at this the next section. In the next section, we're going to learn how to convert from the let's look at this example. We got to learn how to convert from this traditional relay ladder diagram to the PLC logic. Okay, so this is a quite simple one, but you need to recognize all these components before you know how to convert this to a PLC system. So before the PLC, engineers were using this ladder diagram. They call the switch and relay ladder diagram to design a control system for the industrial purpose. For the industrial purpose. So you look at this component here. First, we have the let's start from here. We have the line 1 and line 2, okay, which you can see this as the live and the neutral. So on the live to the neutral here, correct. Okay, so this is a limit switch. I think you learned this before. This is just a contact. So this contact belong to this the coil here. You need to energize this coil for this to change state from normally open to close. So this is a reverse contact here. It's a normally closed. It means when this coil is energized, this contact, normally closed contact, will be open. So we have another limit switch here. One's the name is 14, the one name is 15. So next to this one, we have one called the PS. So PS stands for pressure switch. So this is the pressure switch. You can see it's normally closed. So this is normally closed. And for this SOL stand for solenoid. This should be drawn here. This is the output we need to activate. Is something really similar to the coil. Inside solenoid, we also can find a coil inside solenoid. Okay, so the whole thing, this whole diagram, we will call it switch and relay ladder logic or ladder diagram. So let's read the question here. Draw the PLC ladder. You see, this is not a PLC, right? This is the switch and relay circuit. The textbook calls it circuit, relay circuit, but this is a relay. To me, it looks like relay ladder diagram. But I ask you to draw the PLC ladder diagram, ladder program, and create I/O address assignment table. So we need to create a table, the I/O table with address. For inputs, use address 10 through 47. So we have 10 through 47. Where is 47? 10 through 14, I think 14, not 47, 14. I think you made a mistake. Start the output at address 50 and internal address at 100. Okay, so this the internal we use 100. Internal we use 100, but the output address at 50. Okay, so we can use internal address at 100, but the output we need to use address 50. Okay, and then for this input we can use 10 until 47. So we we just use a few only. 1047 is a many, can accommodate many inputs, but we're not going to use all. We're going to use 10, 11, 12, just a few only. Okay, so first of all, I got to copy the whole thing here to one. Okay, let's copy to here first. I think we need a smaller one will do. It's okay, I think let's use the same size here. So I will call this one, I will call this as, you know, there could be many names you can call it, but I'm going to call it the one switch and relay, because this there's no switch here, but this contact called this limit switch is a type, is another type of switch and relay. Here's a relay, here's a switch. So inside here is only a relay and switch and relay. Later diagram. There's no PLC here, remember? You cannot see a PLC because this is not a PLC. Okay, this is just a switch, a bunch of switches and relay. Switches and relay. This is output. Okay. So first, we need to identify which are the input. See, for inputs, we need to identify all the inputs here. Okay, all the inputs, because we need to create a IO address assignment table. IO is input output, including input output is called IO. So what I'm going to do here is, first let's find all the input. Okay, let's do one by one. We cannot do all at one time. Just do the first one. Let's do the input first. So this is what you're going to do in the exam. You type inputs. Okay, we're going to type the address here. Address assignment. You know, assignment means you need to assign yourself. So the first input, can you see here which one is the input? As I told you already in previously, input are all on the left hand side. Right hand side are all the outputs. So all the inputs are located at the left hand side here. So this is LS14. Let's type LS14. So the okay, and what else? We have let's start from the run number, first run. So we have PS1. So we're going to type PS1 here. PS1, exactly same name, and whether this is a input or output, but you still can treat this one as an input here. It's still the input, because the output is something that on the right hand side. So on the left hand side is the input here. Let's type in input CR10. Okay, we have one CR10 here. I think the CR10 should be on the right hand side here, because this is the internal. The internal of this is not a real one. So we keep the CR10 here. So another one is the LS15. So we only got 3 here. LS15. So for this one, we will assign the address. You see, for input, use address 10 through 47. Okay, so this one, the 10 is a base octal number here. This is not the hex number. So we're going to use a 10. So subsequently, this one will be 11, and this one we've got 12. So we're going to use three addresses for these 3 inputs. Okay, let's create one for the output here. Let's create one for the output. output and address. Outputs, I think I still got space down there. Wait a minute. I cannot move, or I try to move this. Output, okay, and the address here. I can tell you this is the output, but actually this one we can use the internal address. It's not the real output actually. This is not the real output, because the reason why we use a PLC we can write the program. Program is a software. The software actually can replace this hardware. In the old days, before the PLC, you need to use a real relay to do the contact, change of contact here. But when you use a PLC, this part which also used as a latching, you can see this is a latching, right? This can be replaced with the internal memory, internal program. Okay, you can use the internal program here, so it's not the real output. But at the same time, you also can consider as output. So let's put it in first. It's not the real, but it's still the output. Do you get the message? It's not the real output, but still consider output. So the address is start from the real output start from address 50. The internal address start from 100. So this is considered internal. It only exists internally. Okay, it is not any external hardware. It only exists internally, and the real output is here. This is a real one. You actually see it now making sound, making some noise. The solenoid tick tock all the noise. This one is just a one memory bits. No, to keep the state, to keep the status of the output, whether it's on or off. 1 means on, 0 means off. So it's just a one memory bit only. It's internally inside the program, inside the memory. It's not the real output. So but we still need to write down here. So the solenoid is a real output. We're going to use start from 50. So by doing this, at least you know that CR10 is just an internal memory. We can use the internal memory to replace this CR10. Okay, and then we can for the real output here, solenoid here, with this solenoid here, this solenoid 7. For this solenoid 7 here is a real output. We cannot replace with the program. Okay, you need to connect wire. This one you do need to connect wire. This one we can use a program to. We can use a program like a flip-flop, with a flip-flop function to replace this CR10. So this is we call assignment. Okay, this is called address assignment. Okay, so let me now combine these two together. I put it side by side here. Okay, and then I put a title over these two. So the title would be input output address assignment table. So here is the designer need to assign this table. Okay, so in the exam, this you're going to assign this table. So this is the first part you're going to do now to fulfill the requirement stated by this question. IO table input using this address, and then the internal address using this. So this one is the most difficult part for the beginner, is this part. most beginner, they don't know whether this is the can be replaced with the internal memory. This one is a real output. Okay, this is not the real output. This is just an internal memory. I'm going to show you later. You're going to know why I say this is not the real output. So let me put a bracket here. I put a real here. So only one is a real output. This is not the real output. This is the internal. Internal means the memory, the RAM. It's just a memory location only. Okay, so as you know, to design a PLC ladder diagram, draw a PLC ladder diagram. So here we type PLC ladder diagram. So for PLC ladder diagram, I need to start from the input module. Okay, let's copy this. I'm going to draw first. Let's draw the input module first. So I'm going to draw the input module here. Okay, because we've got three inputs here. I think this is enough for three. So let's draw the individual terminal. So I got 10 here, 10, 11, 12. I also need a power supply, 24 volt, and sourcing and syncing. Okay, now let's type the name here. Let's type the address of this input. So we have 10, we have 11, we have 12, and then the next one is a 24 volt, and then we have the sourcing and syncing, or you can call it a common also. You can call it a common also can common. Okay, common. Wait. We also got 0 volt first. For this supply 0 volt, and then we got one called a common. Okay, so we have this one. So the 10 is LS14. So you're going to draw this by going to copy and paste. I'm going to copy and paste this LS14 here. Okay, so the next one is PS1. So I just copy exactly the same thing here. Exactly the same thing. You need to draw exactly the same here. Okay, this is the real input. Okay, you need to do a wiring. You need to connect the wires. This is not the real input. The CR10 is not a real input. Later I'll show you why it's not a real input. But this is the physical real input. You can touch and feel it. Okay, it's a real one. The mechanical parts, you got the internal parts to move when you try to activate. Okay, so we connect this one. We connect this end to the input, to the PLC input. Okay, just like that. Right, we connect this one to input. This one also to the input, to the next input here. To the next input here. Okay, this one also to the next input. To the next input here. So for this end here, we just common together, all common. This is called common here. This is called common. Common. Connected. This. Oh, let me use my pen. Okay, this means connected here. This means connected. This means connected. Okay, now we have to decide whether we want to use a common. We want to use a common. Sorry, we want to use the sourcing or syncing. So for this one, we just use the sourcing. Okay, let's use sourcing for input device. Sourcing input device. So I source from here. Sourcing input device. Okay, so this is sourcing input device. So for input module must be syncing. This is called syncing. we sync the 0 word to the common. It's called syncing. Can you see the difference? So let me show something here. Let me use the red color to show what do I mean here. So here's a source sync. Sourcing input device. All these is considered, even though they are switches, but we call the input device. Okay, sourcing input devices. So the input module is syncing because it's connecting to the 0 word, which is the ground. So it's called the syncing. Syncing input module. Okay, so this is called the syncing input module. All right, so we have already we have done this input wiring part. Okay, we already label and do the appropriate connection, syncing and sourcing, and this is the correct wiring for the these 3 inputs, and then we also do the wiring for the input module. So what next here, what to do next is the PLC ladder in the middle. Remember, we need to draw it in the middle here. Let's see, check the time. So let's start from here. In the middle here, we're going to need how many rung? 1, 2, 1, 2. This is the parallel, so we need to need 4. So the first one here, we got a normally open contact, normally open. So we're going to use a normally open here. So we're going to draw. This is how you're going to draw. I'm going to use a thicker one. First, you can call this L1 also, is okay. Come here, normally open. So if you put LS14, is it correct or not? So you know this is wrong, right? You know why I say wrong? Because PLC program doesn't understand what's LS14. If you're the PLC, you're the CPU, you only understand your own address, your own addresses here, your own internal or your own internal addresses. Okay, so PLC only understand this 10 only. This is the address 10. So put the 10 here. Okay, you can put the name here if you want, because PLC allow you to key in the name, but this name is for you to read, not for the PLC. Okay, this name is for you to read, for the user to read, not for the computer. So what does the next one is this is the AND logic, this contact and this one. So this is normally closed. So we're reaching one critical point here. We need to decide whether we use a normally open or normally closed. So what do you think? Here's normally closed, so we use a normally closed here, because now we're converting this switch and relay diagram to a PLC. So do we need to follow exactly the same normally closed, then here normally closed? Okay, let me tell you, the answer is no. Okay, let me first draw it, and then I'll show you why. I explain to you why is no. You see, you need to use normally open here. So you may ask me, so this is the number 11, right? Number 11. So just write 11 here. So 11 is the address, it's not the name, it's the address. So the name is called PS PS1. You know, when you're using the simulation software, the Logix Pro, the Logix Pro simulation software, on the top you need to write down you need to put the address on the top, 0.0 slash 0, 0.0 slash 1 of this is address and bits, and down below here is a name. Okay, name, if you don't type any name, it's okay. The PLC just don't bother it. Okay, if you don't type the name. So here will be linked to the output. See, output is CR10, but I already told you that this CR10 is not a real output. So what do you mean it's not a real output? It's just an internal memory. It's just an internal memory only. It exists as a memory inside the PLC. So here is just an address 100. So this is just a memory only, just like this one, memory. But this one we got output, and then we need the memory to represent this output. Okay, one more time. This physical input here, we need address to represent this hardware. This one it exists internally. We need address only. We don't need any hardware. There's no hardware needed. Okay, you only exist as a memory. So this is parallel, right? Parallel. System then, you see, CR10 parallel. Okay, parallel. So just draw parallel. Do it nicely. Oh, see, here is some noise here. Okay, draw it nicely here. So I can draw it nicely, or I think you also can, right? In the exam time. So this one is parallel. We call the latching. This is latching, but you don't need to write latching here. Okay. So this is belong to 100. So just write 100 here. 100. It's just a memory here, and this is called the CR10. Oh, do we need to write CR10? I don't think we need to write CR10. I don't need. CR10 stands for contact relay. This is not a contact relay, so we don't want to confuse anyone who read this diagram. What do you want to confuse him that this one is a contact relay? Okay, so we better don't write anything. The more you write, probably you'll confuse the reader. Okay, so this is complete. So let me tell you why this one need to be normally open. You see, this physical input device by default is connected. When you first power on the PLC, you turn on the PLC, this input is activated. This input 10 and input 12 are not activated when you first turn on because they are normally open. Assume there's nobody. Assume this remain open when the PLC turn on. When the PLC turn on, this remain open and this is closed by default. This is by default. Before they do anything, you first turn on the PLC. Normally open here is not activated. Normally open, not activated. But input 11 will be activated because this is already closed. So we have a full. The current can flow from the 24 volt through the PS1 and go to internally. Okay, so the PLC will see this one as activated. When this activated, this one will close. Just like this one, exactly the same. You will close. This one closed, internally also will close. So when you first turn on, PS1 will be closed. Okay. So this is normally closed. So let me put some remark here. This is a bit confusing, but when you do the real PLC, you will not understand. Well, when you do the PLC, you will know 11 will be closed. okay, by default. So what I mean is, when you first turn on the PLC, because this is normally closed, this one will be closed also. You are activated. When this one activated, it's closed, because the hardware is activated. When you first power on, it's already activated. So this one will follow, will close. So exactly the same thing. Exactly the same thing as you see here. This is closed. So this will remain open because the outside will remain open. So it will remain open. This one will close because the outside already closed. So if you put the close, what happens? If you put the normally close here, let me draw it. If you put the close, what will happen? You put like this, exactly the same. You look exactly the same, right? But for the PLC, when you first turn on the PLC see this one activated, and PLC will change this one to open. Then you are opposite. The logic is opposite already. That's why we cannot put it close, okay? Because the PLC will do it for us. We don't need to put the normally close here. Okay, so we come to the second run here. Second run also we got the normally close. This one need to follow. Okay, this one is just exactly something you need to follow the 100, because the logic want it to be normally closed. The logic, it need to be opposite with this one. Okay, so this is the logic here. You know, the question, he didn't say the purpose of this circuit. You just want to convert. So this one need to normally close, just like the original diagram here is closed. Okay, this is a different thing here. This one we don't need to follow, but this one need to follow. So it's a bit confusing, I know. But this one is a logic. This one is not a real hardware. This one is a logic. Logic for normally open, or logic for normally closed. Just like the logic for A and logic for A bar. You cannot change this logic. Example, A B bar. You cannot just simply throw away the bar. Okay, this is the logic. You show the logic is reverse. A bar is reverse of A. So this one we cannot follow. This one is not a hardware. We will follow. So this one is 100. Okay. Next, we got real output. This is a real output. Solenoid is something just like the delay inside the coil. You need the coil to control the like our car door. Every time you deactivate the alarm, you can hear the some kind of tick noise, like tick tack, right? Tick tack, and your door open, right? Tick tack. That is a solenoid. There's a noise created by the solenoid. When use a magnetic force to push the pin, you can see something like tick tack, because they usually use the magnetic force like a magnet to push the thing in or out. That's why you can hear the sound or the noise. So this one is a real output here, solenoid. So we need to draw another one output here. But we cannot use the range solenoid, as you know. We need to use the address. So this is another output, and this is a real output. And the name is, I know it's solenoid 7, right? And then the address is 50. You know, for a PLC, you can use the on the top is the address 100, address 50. So in case you let's say you use another, you add on another new output module, probably the address become 200 for the new output module become 200. So that's how they are using this format for you to in the future, if you want to add on a new output module or add on new input module, they all use the address. So if you use the X and Y, you only can have only one input and one output. So by using address, you can add on as many as you want. example, you can have 4 input modules or 5 output modules, because they all has their own addresses. Okay, they all have their own address. So we've done this. The logic, it looks almost exactly the same except the PS1 here. Everything almost the same, except this one is the normally open. Okay, because it will follow when you turn on. This one will close when you turn on the PLC, and this is not a real relay. In the old days, we need to use a relay to create a logic like this. But on the PLC, we can just use a memory 100, memory. Okay, this don't need to be a delay, because this delay is not going to turn on like the turn on the pilot light. This delay is to control the logic here. This delay is not being used for turn on the any external pilot light. That's why I say we can replace with the memory. We don't need to use the real output. Okay, so now what you left is the output module here. Okay, so we got only one, actually we got only one, which is the 50. We only got one here, 50. More than 30 minutes already. So so assume your output is a 24 watt. Most of the solenoid I think powered by 24 watt. So this is what I'm going to do. So I'm going to write the 24 watt here to power this external solenoid. Okay, you see the solenoid symbol is something like this. Up and down, and that's it, no more. Okay, no more. Up and down here, up and down. So this is the external. We call the solenoid 7. The original name is called solenoid 7. So let's connect this one to 24 watt. So called the sourcing external, sourcing output device. Okay, and then here is our 0 watt. Every power supply comes with the positive and the ground 0 volt, right? And also come with this common. This common is used by the this module, output module. So when this one is sourcing, this one must be syncing. The output module must be syncing. They need to opposite each other. So this address is what? Is 50. Remember, 50 is the address assigned by the designer, and follow this requirement. Output start at address 50. So here's 50. Okay, so you need to do it slowly in the exam. So you see that there are no overlapping. 10, 11, 12, 50. They are not overlapping, and 100 for the internal memory. This is input. Sorry, one more time. Input. Start from 10. Input. Start from 50 is a real output. We're connecting to the real external output. Need to use a 24 to power this output. But the relay is not real one. See, there's no relay here. That's why I say it's not a real output. It need to be here internally only, as an internal memory to provide these two logic. So when you turn on this, I change these two. So this functions is really simple. If you are this 100, if you are this delay, when I turn you on, you help me to close this one, you help me to open this one to control this. So I don't need a real delay for this purpose. So this will be the answer for this question here. So I hope you can follow, right? So let me I think that's all, right? That's all. This is the answer already. So the answer consists of the address assignment table So you earn about 10%, 10% out, or 20% of the total marks here, and then the remaining marks goes to this input module, output module, and a PLC ladder logic. This is called ladder logic. If you call it PLC ladder, that can also correct. I think this is the answer. I don't need to draw and write down anymore. So this is the PLC one. So we'll continue with the next example here. This I'll end video before it's taking too long here.